Hi, I'm Sujai from UW-Madison, and I'm here to talk about our work on improving performance of recoverable applications that use persistent memory. We call our work ASAP, a speculative approach to persistence. Intel's Optane persistent memory packs various features, amongst which are byte addressability and non-volatility. This allows persistent memory to support a new class of applications that can have recoverable in-memory data structures. Correct recovery, however, requires that memory is in a consistent state on a crash, and this imposes an order on the writes. Now consider an example of a pointer pointing to some data. The cache could write back the pointer before the data. If the system crashes at this point, we have pointer pointing to incorrect data. For correct recovery, we require programmers to express the order for their applications, which the hardware must enforce. Now, systems today achieve this using flush and fence instructions. Intel's CLWB writes data back to memory from the caches, while the sfence instruction stalls the core execution until all prior flushes complete. Now, past research has shown that such a form of synchronous ordering can cause drastic slowdowns up to 4x. Now, researchers have tried to mitigate this, and one such solution is buffered persistency. In these designs, the hardware includes a circular buffer that queues writes to persistent memory. This buffer tracks the ordering dependencies between writes and flushes them lazily and in order. The main advantage is that persistence is now decoupled from the core execution, hence avoids any core stalls. We, however, identified a couple of drawbacks with these designs that don't allow them to scale. The first is to do with ordering writes across memory controllers. Now, these designs use conservative strategies that do not allow them to overlap flushes to multiple memory controllers if they are ordered. Therefore, these designs are not able to fully utilize the write bandwidth in the system. Similarly, when writes have to be ordered across threads, these designs stall flushing in the dependent thread until flushes in the source thread complete. Now, this can cause the buffers to get filled up quickly, which in turn could exert back pressure on the core by stalling them. And from our experiments, we saw that cross-thread ordering can be quite frequent in some applications. We propose ASAP, a buffered persistency design that overcomes the mentioned limitations. Crashes are rare compared to the frequency of ordering events, so ASAP takes an optimistic approach to flushing. Writes are flushed eagerly, which are then used to update memory speculatively. ASAP saves enough information to correct memory in case of failures. One of the key insights is the feature of Intel systems today called ADR, which allows some of the data to be persisted even after a power failure. ASAP leverages ADR to store the fix-up information. One of the core design principles in ASAP is the concept of eager flushing. But before we get to that, I want to define the term epoch. An epoch is a set of writes that have no ordering dependencies between them, so they can be flushed concurrently. Now, epochs are ordered using fences, and writes in different epochs need to be ordered. Now, let's get back to ASAP. Unlike prior designs, the persist buffer in ASAP flushes writes eagerly, almost immediately without waiting for earlier epochs to complete. Now, the flushes are, however, differentiated as safe or early. Now, how does it do that? Well, ASAP uses another hardware structure called the epoch table to store metadata of ongoing epochs. This table tracks ordering dependencies, including those that arise across threads. It helps the persist buffer mark flushes as safe or early based on the status of earlier epochs. Now, why is this distinction required? Because of the memory controller in ASAP treats them differently. Safe flushes are treated like normal flushes in systems today, but when an early flush arrives, it tries to update memory speculatively with this value. But before doing so, it reads the old value from memory, creates an undo record, and stores such records in a structure we call the recovery table. As mentioned earlier, the ADR domain is extended to include the recovery table in the memory controller. In case of a failure, the recovery information in this table is used to unroll the effects of speculative updates. To tie it all together, in ASAP, writes in dependent threads and dependent epochs are flushed concurrently, and some of them are marked early. The memory controller updates memory speculatively with these early flushes after creating undo records. And ASAP also has mechanisms to communicate epoch completions to the memory controller and dependent threads. We implemented and evaluated the performance of ASAP using Gem5. The code has been open sourced and is available online. The graph on this slide shows various workloads along the x-axis and the speed up normalized to the Intel baseline systems on the y-axis. For applications that with large number of cross-thread dependencies, prior designs are unable to achieve high speedups compared to baseline. ASAP is, however, able to flush writes from all threads concurrently and therefore improves performance by about 27%. We also compared ASAP to an ideal system like Intel EADR with persistent caches. We saw that ASAP is able to achieve similar performance without requiring large batteries. For more details and results, please read our paper. I would be happy to take any questions or talk more about ASAP now. Thank you for listening.